We would like to present our research work adhesive strength of an epoxy-based adhesive joint under a complex stress state. Polymeric materials find an ever-increasing application in various industries, this being favored by the improvement of production methods and the use of various modifiers. The development of methods and procedures for evaluating various performance characteristics of these materials is becoming important. The use of arcing devices is promising for studying adhesive failure under the tension plus shear loading condition. The aim of this study is to test a modified arcing device for investigating the effect of the stress state on the adhesive strength of the epoxy aluminum alloy junction. The paper studies a polymer coating its substrate system in the form of modified arcing specimens. Polymer interlayers were made from glue based on Ad20 epoxy. The substrate system was produced from a hot-rolled plate made of the aluminum-magnesium-lithium alloy used in aerospace industry. The polymer coating was applied onto specimen halves, which were then joined together and left for 24 hours for polymerization at room temperature. The testing was performed on a Zwick Rowell universal testing machine. The prepared specimens were mounted in the grips of the machine, and the angle alpha between the tensile direction and the normal to the junction plane was varied. The angles considered in the work are shown in the figure 2. As the angle was varied, the stress state patterns were changed. Alpha equals 0 peel under the action of normal tensile stresses. Alpha equals 90 degrees shear under the action of tangential stresses. At the intermediate values of alpha there is a complex tension plus shear stress state. The change of the load R was recorded during the testing. The loading diagrams are linear dependences. Consequently, failure occurs within elastic deformation of the polymer coating. Suppose the stress state at the epoxy substrate interface is homogeneous. Therefore, to evaluate it, we use the average values of normal sigma and shear sigma as stresses. In Formula 1, Pmax is the tensile load corresponding to the moment of adhesive joint failure, or failure load. S is the area of adhesion. The formulation of the local failure criterion uses the assumption that the strain energy density in a selected microvolume including the joint is the driving force for the delamination of the adhesive joint under a force action. For this purpose, a microvolume simultaneously belonging to the glue and the substrate is conventionally selected on the joint, which is inside and along which slippage and delamination are prohibited. The values of the strain energy density components Wn and Ws in the selected microvolume are calculated by formula, where E and G is the normal elastic and shear modulus respectively. The formulas 3 can be used to find the effective values of the normal elastic modulus, the shear modulus and Poisson's ratio for the selected microvolume under a plane stress state in the first approximation, where H1, H2 are the glue and substrate layer thicknesses in the selected microvolume. E, nu, G1 and 2 are the values of the normal elastic modulus, Poisson's ratio and the shear modulus of the glue and substrate materials respectively. Assume here that the ratio between the values of the thicknesses in the selected microvolume is equal to the inverse ratio of the values of the normal elastic moduli of the glue and the substrate. Substituting 4 into 3. After simple transformations we arrive at the formula as 5 for calculating the effective values for the selected microvolume. Table 1 shows the experimental values of the failure load for each angle alpha and the coefficients of variation. It is assumed in statistics that the degree of data dispersion is considered to be insignificant if the coefficient of variation is below 10%. It is obvious that for most of the angles, the data dispersion is insignificant, this being indicative of experimental data repeatability. Therefore, it is possible to speak about the repeatability of the experimental data and about the applicability of arcing specimens. Table 1 shows the values of sigma n, sigma s, wn, and w's calculated for the averaged values of Rmax. The figure 3 shows graphical interpretations of the data from Table 1. Table 2 presents the limit values of strain energy density Wn asterisk under pure peel, alpha equals 0 degrees, and W's asterisk under pure shear, alpha equals 90 degrees. The values of Wn asterisk and W's asterisk have been calculated by Formula 2 for the average values of sigma n and sigma s from Table 1, and they are quantitatively similar. For a complex stress state, when the peel and shear stresses act simultaneously, ratio between Wn asterisk and W's asterisk and adhesive failure are described by straight lines in the diagram's figure 4. The equations of the approximating straight lines in figure 4 can be written in as Formula 6, where the fraction denominators are equal to the lengths intercepting the straight lines when crossing the coordinate axes. These lengths are equal to the values of the strain energy density components at failure under peel Wn asterisk and shear W's asterisk from Table 2. Equation 6 has the meaning of the adhesive failure criterion under the tension plus shear complex stress state. Note that the linear failure criterion similar to 6 is used to predict crack propagation conditions, but with energy release rate Ge used instead of strain energy density. Experiments with modified Arkin device have been made with a variation of the load application angle. It has been demonstrated that this method is applicable to estimating the effect of the stress state, that the experimental data are repeatable, and that the degree of data dispersion does not exceed 10% for the most part. The analysis of the results has enabled us to formulate the linear failure criterion. The proposed method can be used for plotting diagrams allowing one to determine a safe stress state, not leading to adhesive joint failure.